All right, this is part 2 of chapter 8 of Applied Statistical Analysis for Psychology and Human Factors in R. And the part 1 video is here, the part 2 video will be here when I complete it, and you should be able to go here to download the materials for this. Mostly what you need is this walkthrough document if you don't want to type in everything I'm doing. So you can go and download that. I've downloaded it myself and I've opened it up here. And the first half of this, so we're about around line 200 is where the material for this part starts. And so today we will continue what we were doing before, thinking about simple hypothesis testing. But all we did previously was sort of cover the theory of this and look at one sample test, like the one sample t-test, the one sample sign test, and a Bayesian one sample t-test. So we're going to continue and cover paired tests, paired t-tests, and also independent samples t-tests, and then move on to tests of correlation and tests of categorical association, and then finish with some other issues like how to compute effect size. So this is the same sets of values that we've dealt with before that are over here on this these violin plots on the right. We're also going to create, so I just copied this down so you have exactly the same numbers, and we are also creating a new one, so we can just look at hist of x0b, which has some relationship to x0. If you remember, right, x0 has a mean of 0, so this is equivalent of a null hypothesis distribution. But now x0b has a relationship to that. So this is as if you did a pre-post test. So the question we're going to be dealing with today is what happens when you have two observations of the same person, condition, subject, or case, or if you have linked records somehow. So you may have a medical test of medical diagnosis or medical intervention, and you have age matched controls, and so you want to see if it has an effect, and then you have someone without this disorder, but they are the same age and education matched. And so you want to take advantage of the fact that there may be systematic differences across your sampling population, and you only want to measure the change either before or after or between two matched samples. And so here we see that, if we look at plot of x0 and x0b, they're created so they're highly related. Their correlation is very strong, even though there is some noise. It's really not much, and it's almost a complete straight line. So but the difference is not much. So if we were to look at, I don't know, if we did a violin plot of x0 and x0b, we have to load. I think it's called vioplot. Now if I do a vioplot of x0 and x0b, here we go. They look almost identical, right? So even though there's a strong correlation, so the person who's way up here is also way up here, the distributions look almost identical, and we would have a hard time telling them apart. So this case is very much like the one sample t-test. So I've got two samples, but they're linked. And so what I always can do is calculate the difference between them and do a one sample t-test. And so I could, even though they're very different, I could do x0b minus x0, and that would give me sort of how much improvement was made. And if I want to do a vioplot of that, x0, I'll put them all three on here. we can see that even though the overall pre and post distributions are very similar, the shift in these is very slight but mostly positive. And so we may be able to detect this small difference, this small improvement, even though the overall differences are large. So you might think, well, this could be a developmental study, and these are their overall average sort of z-score before and after. So you have 5-year-olds and you have college students up here, and maybe there's some training intervention or some meditation intervention to prevent math anxiety on a test. And even though you would never expect the 5-year-olds to do as good as the college students, everybody does a little better. And so we may be able to test that. So the easiest way to do a, a paired t-test, a paired test, is to do a one sample t-test on the difference. So we can do t-test of this, and we can see that, oh, this is, the t is very large, it's highly significant. As we'll cover after this, if you have independent samples and we wanted to do x0 versus x0b, here we don't see a difference. So if we do a t-test between these two, we don't see a difference, but because we have repeated measures, when we subtract the two and do a one sample t-test, we do see a difference. Okay, so we can always do a test like that, a one sample test. That's exactly the same thing as telling t-test to do a paired test. So we can look at, here's the one sample version and here's the paired version. Now it says one sample paired, but the t-values are all the same, the degrees of freedom are all the same, the p-values are all the same, everything's all the same. So really it's an identical test, and you can do it whichever way you prefer. But if you forget to give it, if you forget to tell it paired, then it gives you a different number, and now it's no longer significant because it's saying, I want to know if this distribution differs from this distribution, but there's no way I know which observation here is linked to which observation there. And so if it says Welch's two sample t-test, then and you're trying to do a one sample or a paired t-test, you've done the wrong thing. You haven't put the paired in. So be careful that you make sure you use this appropriately. It's also incorrect to use this if it's not paired. And so be careful that you understand what this argument is. There's also, it can get confusing because there's pairing, but then there's the alternative option. Do you want it to be one-sided or two-sided? And if it's one-sided, do you think it'll be less or greater than? And so here's a one-sided paired t-test. So I've asked, because I think my intervention should improve things, I'm only going to care about if it makes things better, and here the p-value is very small. If I reverse these and used less, so the p-value is very large now, and I don't see any evidence of a change. So the idea would be, well, I think things in this case are going to get better. And I know that because of that, I've subtracted, so if you do mean x0b minus x0, you see it's positive. So I think things are going to get better. So the alternative less means that the first one's going to be less, or the second one's going to be less than the first one. Or, I'm sorry, the first one's going to be less than the second one. And so I can have even more power, and you can see that let's see, if I do this again, the p-value here is going to be smaller for the same t-value. The t doesn't change, but the p-value when I do the test changes because now I'm considering both tails here, but only one tail here. So you just so in this case, it's okay to do the one-tailed because whether or not it goes down or stays the same, I don't care. The treatment is ineffective in either case. So I just want evidence that it's going up. All right, so there's certainly the same thing can be done with all the different t-tests, all the different varieties of t-tests. But previously we'd done a sign test or a binomial test. And so if we load this library again, basic, what was this called? BSDA. So I will reinstall this, and this includes the sign test, which is identical to this binomial test. So I could do library BSDA, and now try sign test of x0 minus x0b. So that's the same as this slightly more wordy version, or in fact I calculated diff so I could do a sign test on diff. So now this is still highly significant. I get 7 cases that match the sign difference. 7 out of the 20 were higher than 0, and that p-value is very small. But if you compare it to the p-value you get for the t-test, the paired t-test, this is much smaller. So you still have much more power here, most likely, than in the binomial test. But here, the binomial test and the sign test should give us exactly the same p-value, and number of successes is 7. S is equal to 7. P-value is 0.005. P-value is 0.005. But if you have a paired samples t-test, actually there's a more powerful non-parametric, and that's using the Wilcox test. So the Wilcox test, what it does is it sort of figures out the relative positions of all of your pairs. And so if you look more closely into this distribution, it punishes you more if you have not just things less than 0 or greater than 0 like the sign test is, but if it's more or less than 0, relatively speaking. So if you only have one thing less than 0, but it's the first thing less than 0, that's going to be less evidence against than if it's the last thing less than 0. So the Wilcox test is not going to be the same as the sign test. For a one sample test, there's not really much you can do, but for the Wilcox test there is. So but here, so we can see that for the Wilcox test, the significant value is much smaller than for the sign test. So, and the Wilcox test doesn't really care if you give it, it doesn't really care if you give it a pairing or a single value like the one sample test. So these are then two alternatives to use. Oftentimes the sign test is used because it's very simple, and the Wilcox test is a little harder to understand, so people just use the sign test even though the Wilcox test will be more powerful. Okay, and then you can always use the t-test Bayes factor as well, and we can give it t-test. Oh, let's look at what Wilcox test if I don't say paired. So now, if I don't give it a paired, this is not significant anymore. And so that's clearly, you have a very systematic relationship between these two, and ignoring that systematicity, you won't find that systematic relationship. So you want to make sure you use paired properly here. And we can also, let's see, we can also do a one alternative or two side or two alternatives. So you can also do paired is equal true, and then alternative equals less. Alternative equals less, because I've reversed the order of these. That's the wrong one. And now this is even more powerful because I'm expecting an increase and I can detect the increase if I do a one-sided test. Okay, so you can always do a base factor test too, using the same logic, either a delta score or the paired. So now, if we look at the results, we've got the alternative hypothesis. It's got a value of 30, a base factor of 30, so we strongly favor the alternative. This would be strong evidence, or this would be maybe not overwhelming according to the tables we've looked at before. If we, let's see, I've got to undo my full screen. And if we bring these tables back in, again, positive support for the null. Oh, I was confused. We're at 30, so we're at in the strong support for the hypothesis zone. 30 is really strong. So now if we try to do it just by doing the change, we get the same number. And in fact, I don't think the results look any different. They don't even, it's both of them are the base factor one sample underlying test. But if we want to do a one tail, we have to specify the null region. And so I would say, well, since we have this difference and we expect an increase, all of the increases are going to be negative. So if we make the null interval 0 to 10, we now have even stronger evidence. This is the one tail test, and the evidence for the null is very weak. It's 1 in 20, which is very strong evidence against. The evidence for the alternative is very strong. It's now 60. So we can gain even more power by coming up with a region that we think would be reasonable. Now I picked 0 to 10 because there's really nothing less than 10 that's going to happen. But I haven't figured out a way if you can actually sort of specify an infinite range. I think if I do like inf, let's see, an R is inf like this. So if I do 0 inf, I guess it handles that. Except I wanted negative inf. Here my alternative is 0 to inf was my alternative, and I get strong evidence versus the opposite. And if I do negative inf, it just reverses these. Okay, so you can use inf, but for infinity, but you have to use capital INF to represent that range. So again, we can see really overwhelming support for the alternative hypothesis and strong evidence against the null hypothesis here. Okay, so I covered the paired tests first because they're almost identical to the one sample tests, but really they use the same tools that the two sample test does. So let's think about a two sample test, and we'll consider the t-test for now. You remember earlier we needed to calculate a t-test, a one sample t-test. We needed to calculate the mean difference from 0, and we calculated the standard deviation of that, and then we calculated the standard error of that. Now we have a little trick trickiness here because we've got two means, and we can calculate the difference between these means no problem, but we also have two standard deviations, and I'm looking at x1 now and x1a, which are different sizes, and so I want to highlight that one only has 20 and the other is 200, and so I'm doing this because the independent samples t-test doesn't assume there's any link between your variables, and this makes it very clear. Even though this is my first observation, it really has nothing to do with this. These are independent measures, and in this case I happen to be able to measure many more in x1a than in x1. I've seen this, for example, you may have done some study where you've got managers and the manager, or people who are working, and so you have, there's going to be maybe a 10-to-1 ratio of managers to the people they're managing, and so if you want to see the differences in perception of managers, you're never going to be able to collect as many managers as you will the people they're managing. If you go to any workplace, you'll just get more of these naturally. And so there's no reason to collect the same number. You want as good of an estimate of both of these as possible, but you just might not be able to get this. So in a paired test, we have independent measures. We have sampled these two distributions independently, and there's no linkage between the particular cases, like in the paired, or when you transform the paired into a one sample, you take the difference. We can't really take the difference between this and this. But so we can take the difference between the means of these. I can calculate the mean of this and the mean of this and take the difference. And I can calculate the standard deviation of this and standard deviation of this. But now we have a problem because we want to calculate the standard error, divide the mean by the standard error to compute our t-test. Well, how do we do that? Well, it turns out that you can come up with principled ways of combining standard deviation across groups, and it's going to be a sort of weighted average. So to compute a pooled standard deviation, we compute the variance of the two and the size of the two, and then this is sort of a weighted average. You calculate the square root of the variance divided by n and variance 2 divided by n. This calculates the standard error. And so it's dividing each of the variances by the square root of n, but then pooling them together. And it turns out that variances add when you do this. So this turns out to be a reasonable way of estimating a pooled standard error for these two groups. A reasonable and principled way. But you're still just sort of finding the average between the two. And so you always then have to worry, if you're doing this, if I really have many more in this group than in this group, some of these variances are going to get washed out by the variance in my other group. So now I can calculate my independent samples test by taking the difference, dividing it by this pooled standard deviation. My t-value here is going to be negative 1.06 for the pooled, and so you should recognize that this is not going to be significant. I can look this up on a t-table. Well, the p-value there is 0.147. And we'll look at this in just a second. Okay, so here I would say it's not significant. T is equal to t on 38 degrees of freedom is equal to negative 1.06 or 1.06. Unless you're doing a one-sided test, the absolute value really doesn't matter because the t distribution is symmetric, and 38 degrees of freedom, this is the t-value, this is the p-value. It's not significant. So I should be able to get the same number here if I tell it a t-test with x1 and x1a. Alternative is equal to less. So here I can see, well, my t-value is the same, but my degrees of freedom are a little different. Here I said it was 38. They give this weird degrees of freedom, 23.7, and a p-value of 0.149. So if I look up t-test, you can see that there's this assumption var equals false, so I don't actually assume that variance is equal. And let me see what happens if I set that to true. Now it gives me also a very different number because it's not doing the pooled variance in the same way. But if I'm convinced that my variance is equal in my two groups, I can set this equal to true and maybe get more power. But I'm also, well, I can't really understand. I don't know what the variance equals to true is actually doing here. But I think it's going to be using a different formula for pooling because here we're allowing these to be different, and so what it may be doing is subtracting the mean from each one and then just pooling them to create the variance rather than calculating the variance separately and pooling them by weight. So 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 let's see. So if we go back to here, we can see it says Welch's two-sample t-test, and the Welch two-sample t-test is one where it recognizes that you may have different numbers of observations in each group, and the variances may be different, and it tries to correct for that. So the t-value stays the same. It uses this as the pooled measure of the t-value, but it comes up with an adjustment for the degrees of freedom. So even though I had let's see, x1 and x1a, even though my degrees of freedom here was 23, it's going to correct it down to, I'm sorry, even though my degrees of freedom was 38, actually I don't know why I thought it was 38. Let's see, let's look at this. So x1 has 20 and x1a has 200. So I've used 38 here for no good reason at all. I've got 20 in one group and 200 in another group. If I had 20 in each group, then 38 would be the right number. But the question is, what's the right number when you have mixed groups and you have different variances? And that's a tricky thing to even answer. If I assume they're going to be the same and use the variance equal, you can see that my degrees of freedom for the variance equal condition was 218, which is 220 minus 2. So that's actually probably what I should have assumed in this t-value. So 218, and I get a p-value of 0.145, and let's see if that matches up to the variance equal assumed. See, that's still different because they use a different measure for pooling the t. I'm still using the 1.06, and the t, when you assume it's the same, you don't use this formula for calculating standard error. Now, what the Welch's test will do is come up with an adjusted value for your degrees of freedom. And even though I had 200 in one of these groups, it thinks, like when it's doing the adjustment for this, it's saying, well, 23.7 is the right number of degrees of freedom here, because it's going to be highly biased by the thing that you have the fewer observations in. Since I have 201 of them and 20 in the other, like I could have 2,000 in the other one instead of 200, and it wouldn't improve my degrees of freedom much, because most of my variability is really in my smaller group. So you don't get a huge advantage by collecting much more in one group than the other. You get maybe a little bit of advantage in terms of these degrees of freedom, but not a lot. And I think that makes sense. If I had a million in one group, then it's essentially doing a one sample t-test, right? And so if I had a million in one group and 20 in another group, it's like doing a one sample t-test against the mean of the other group, and then my degrees of freedom would be 19. And so this correction might not even really be right, if you take it to that extreme. So for for this, well, just two sample, the degrees of freedom are going to be highly biased by the group I have fewer of in. And so if you have unbalanced group sizes, the intuition is, well, spend your money and time making them as equal as possible, collecting data in the smaller one, because that will have the best advantage of the power for the power of your study. But if I look at what these degrees of freedom that the Welch's procedure does, and there are formulas for calculating this, I'm not going to go into that because you usually wouldn't calculate it on your own. But I can put that same t-value here and get exactly this 0.1499. So the Welch's test uses the standard error formula for calculating the t-value that I've put here. It uses some other formula for calculating degrees of freedom, and then it looks it up in the same t-value. So the only thing that's sort of mysterious here is this guy, and since you're going to use the t-test probably to calculate this, you can, if you need to, you can look up what is the weighting formula for the degrees of freedom that the Welch's test is doing. You should always report that if you're doing this, that you're using a Welch's two-sample test, because that's going to be different than a standard two-sample t-test that doesn't make these assumptions about sort of punishing the degrees of freedom. All right, so next, that's the two-sample t-test. When you have independent samples, independent or two-sample t-test, you can do the same thing for using the Wilcox test, and I think I've got some additional examples here. So I can do the Wilcox test between two values, and if I do, I guess I'll do the Wilcox test first between x1 and x1a. I've got to spell it right. And you can see, again, this is not significant, just like this was not significant. And the p-value here is larger than the p-value if I do alternative equals less, just to put them on equal footing. Well, it's actually very close. It's maybe a little smaller in this case. In general, because the Wilcox test is not just looking like at a sign difference, but at all the different rank orders, all it's going to do is sort of be a little more robust to long tails that might impair the t-test. And so I think generally you get a very similar p-value out of the Wilcox and the t-test. And when, especially if you have sort of regular normal data, I mean, if you had data that were uniformly distributed within some range, you'd probably get almost identical numbers. And so the way they're going to differ is when you have a long tail that sort of may distort the variance estimates for the t-test, but it won't be distorted for the Wilcox test. In fact, generally when you do a two-sample independent samples Wilcox test in R, this is referred to as a Mann-Whitney U test. So if we look up, it says a Wilcoxon rank sum test. Wilcoxon is the null distribution it's going to use it against. And if we look up Wilcox test, it will say performs one and two sample Wilcoxon tests on vectors of data. The latter is also known as the Mann-Whitney test. So the U is the statistic of the Mann-Whitney test. So it's often in psychology reported as a Mann-Whitney U or Mann-Whitney test rather than a Wilcox test. And you could report it that you used the Wilcox test function in R to compute a Mann-Whitney U test. Okay, but so the question is, well, how does this Wilcox test work? And I've got a little example here. So here I've got, similar to before, I've got a set of x values and y values that are independent, but the y is slightly larger than the x. And what what the Wilcox test does is it looks at every possible pairing between every x and every y. These are independent samples, so they don't have to be the same length. There's no sense in which the first one is associated with the first one in the other data set. So to do this, I can use this little outer function, and this will look like magic if you've never used it before, but if I look at pairs, what it does is for every pair of x and every pair of y, it does this test. It says, is x greater than or equal to y for this? And so I've got, every case I've got trues and falses to say if it's greater or less than. And if I add these all up, I get the number that are greater than 115. And of course, there's 20 in each. 20 times 20 is 400, so I've got 115 out of 400. And now the Wilcoxon distribution just asks if I have 20 items and they're randomly distributed, what's the distribution of this that I might get? And what's the likelihood of getting 115 or fewer, or maybe the opposite of 115, which would be 300, 285 or more? So I've got the sum and the length, and I can do I can look it up with the P Wilcoxon or P Wilcox, and it's going to be in this case 115 2020. And so in this case, what I set is actually highly unlikely to be have occurred just by chance. It's basically a 1% chance that it could have occurred at random. And so this would be fairly strong evidence. I can plot both the density and cumulative distribution. So if you look here at 115, that's right about here, and you can see it's far enough in the tail that it's unlikely to have happened under the null hypothesis. And I could look at the cumulative, and again, either 115 or 385, which would be about here, is way in the tail. And so in this case, we would reject the null hypothesis here because it's unlikely to have happened just by chance, according to the Wilcox test. That's all the Wilcox test is doing. It's looking at all possible pairs and adding them up. And so you can see that any transformation that retains the order of these is going to have no effect. So if I do okay, Wilcox test less is 0.01. If I do the same thing and I do a log transform of each of them, I think I can do that. Oh, I can't do that, but I can do log of 10 plus x and log of 10 plus y. You can't take a log of a negative number. So if we do this, we can see that we get exactly the same thing. I've done a transform that's doesn't distort the rank order, and I get the same thing. So even if the histograms of these, the hist of log 10 plus x looks very different than the hist of x. Well, it looks somewhat different. It doesn't look too much different. But even though I did a transform, it preserves the order, so nothing changes there. Actually, the t-test and the Wilcox test both have alternate ways of applying them, which is more like you might run a linear regression. So if I, instead of having two different columns of data, so I had x1 and x1a, if I put these together, or I had x and y, I could put these together and label them. So I have maybe a data frame that has ones and twos, and a values which is just the values. So this could be in a data frame. It doesn't have to be. I could do a Wilcox test and actually a t-test the same way. So I could say values tilde groups, and I'll get the same number. And I actually could do a t-test of values tilde groups and also get the same number. This is useful if you have your data, especially, you can't do this in a paired test, but if you have an independent samples t-test, oftentimes your data are going to be arranged like this. You will have a bunch of rows, each representing an individual, and you'll have a variable that says what condition are they in or what group are they in, and you'll have their outcome. And you can do it this way to avoid having to pull out those particular values and do it separately. And so finally, you can do an independent samples test with the Bayes factor. And we had both a couple different methods. Lost it. T-test Bayes factor is 0.36, so this is right around the value of, it's in the ambivalence region, and it's right around the value of fairly strong evidence for the null. I could do X and Y like I had before, and here's strong evidence for the alternative. And of course I could X, Y, and then put down the null interval. And I'm not sure what you would put down for the null interval here. Well, I've put it here, and it finds strong evidence for the alternative that's outside of this range. I guess it looks at the difference, and so my difference between these is X minus Y. It's going to be mean of X minus Y is negative 0.21. So you might want to do something like, I'm going to say the null interval is 0 to inf, and that will give me a one sample test here. So 0 to inf has strong support against. A negative change has pretty strong support for. Or you could say, well, I think that anything between negative 0.1 and 0.1 is no change. But if it's bigger than that, I could make money on it, or I could do that. Then it's worth impacting, and so I could have a null interval that's sort of around the zero change. And you can see that here, it's ambivalent about there being no change, but it's strong evidence that it's outside of that. And this would still be a two-sample test, or a two-sided test, sort of, because if it's less than negative 0.1 or it's greater than positive 0.1, it will still provide evidence for it. All right, the next topic. So that's 3 examples of how to do independent samples t-test. Previously, that was 3 examples of paired t-tests for both t-tests, rank order, non-parametric tests, and Bayesian tests. Now, maybe one of the most common things that you do for simple data analysis is to look at correlations. And so let's figure out what correlations, what a correlation actually means. So I'm going to take a set of data, and I'll sample 1,000 points from this, and then I'm just going to write the function for variance, the variance function. So the variance function is really simple. I find the mean of the values, I subtract each one from the mean, so I have a delta. Then I square all of those, so that's so x minus mean x is going to be the error, squared error, this is going to be the squared error, and then I'm going to divide by n, actually divide by n minus 1, because that's the sample standard sample variance function. And so it's sort of mean square error is what variance is. There's nothing complicated about this. It punishes larger deviations from the mean more than smaller deviations, and the same deviation, if you add up two small deviations, is punished less than one large deviation that is the same, that is the sum of the two small deviations. So it's convex. It's a convex cost function, really, as well. But this is variance, and I can calculate variance of data, and I can calculate the sample variance of data. And as long as I have defined my function, which I didn't load it, you see these are exactly the same. So variance, the built-in function variance, is the same as does the same thing I did here. Okay, so I'm going to take this in a couple pieces. I'm going to rewrite my variance formula. So instead of taking square, I'm going to take this and multiply it by itself. This is exactly the same thing. X minus mean x times x minus mean x is the same as x minus mean x squared. This is a little less efficient, but I'm going to just build this, and just to convince you, I get exactly the same number. Okay, so I've done that, and now that I have these separated, I could rename x in the first part and x in the second part. And because I'm convinced they're the same size, I could then just still divide by x, but I could divide by x or y here, the length of x or y. And so I'm going to separate these out and put the first part is x and the second part of this formula is y. Everything else stays the same. But now I have to give it my data twice. So this seems like it's even less efficient, but just to convince you, I'm getting exactly the same number here. Okay, so now let me take this formula and I'll calculate a new set of values, y. So if we plot x versus y, you can see that they are negatively correlated. The correlation is visible. You can see that there's a difference, but it's not very strong. And if we and so maybe we want a measure of how strongly these are correlated. So we could think, well, I could see the variance in one of these by putting this with itself. But what if I put these together? Now what I've done is I'm gonna, for any point, I'm going to calculate the difference from the mean, and then the difference. Here's the mean of x and here's the mean of y. So for any point, I'm going to calculate the difference from the mean of one and then the difference from the mean of the other. And so if you think about what's going to happen, if everything is on this line, or let's think, if everything's on this line, then what we'll have is there's going to be values that are large negative, calculated by other values that are large negative, and values that are large positive combined with other values that are large positive, and they're all going to be divided. In contrast, if I have something over here, and so that's going to be a very positive number. If I've got a bunch up here and a bunch down here, like in a cross, then everything up here will be balanced with something here that gets subtracted. So I'll have a large positive times a large positive, and then that might be balanced with a large positive times a large negative. These will cancel out and it will be closer to zero. So if I have like an X pattern, you'd expect that this formula will produce something closer to zero. If I have everything along this positive diagonal, it'll be very large positive. And if I have it on the negative diagonal, I'll get large positive values times large negative values up here, and large negative values times large positive values down here, and I'll get a large negative number. So I'm going to just calculate, I'm going to rename var sample 3 to var sample so I don't have to reuse it, that 3 all the time. And I get a value of negative 9.3. So what does that mean? This is our estimate of the covariance between these two. So if I were to do covariance of x and y, I get exactly the same number. So there's nothing magical about covariance. It's just it's just a way of taking the average value, subtracting on one dimension the value from the average value, the other dimension the average value, finding the product of those two, and then finding the average of that product. And it's almost the same as variance. It's just It's just a generalization of variance or mean square error. So it's called covariance because it's a variance of two things. Oh, here's the same plot, and it's got a covariance of negative 9.7. And we can see what happens if so covariance of x and y, but if I reverse one, if I make one negative, it's the same value, but it's positive. And maybe that doesn't, maybe you don't have intuition for that, but if I plotted x by negative y, we'll see that it's got a positive relationship. If I plot x by negative x, we see that it's got a negative covariance. So this is just the variance of x, but it's negative. And so this gives us a measure of the relationship between two variables, but sometimes we want something else because this depends on the scale of the two. Like if I multiply one of these by 10, the covariance is 10 times larger. So it's hard to know what the covariance is. The covariance high or not in sort of a scaleless way. It always depends on the scale of the variables. And we'd like to come up with a way of normalizing this because this sort of relationship seems like it's pretty strong but not super strong. And can we have a way of normalizing this? And so what we do is we can come up with a normalized covariance. So we calculate the covariance just the same way we did before. And what if we take this covariance and divide by the variance in each row? So I take the variance, I calculate the variance of the two, and then divide. So you're punishing it only by its contribution. We divide the covariance by the square root of the variance in each direction. Okay. So now we have this normalized covariance, and it's negative 0.41. And you can see, because if we feed x to x, if we feed it two of the same values, it's going to compute covariance x to x, which is just a variance, and then it's going to compute variance x and variance x again. It's going to divide the covariance of x, or the variance of x really, by the square root of the variance of x and the square root of variance of x. So this is going to cancel out, and it's going to equal 1. So the maximum this can have is a value of 1, or if it's negative, the minimum it can have is a value of negative 1. So now I have it's minus 0.41. Let's look at the values again. So we know that it's negatively related. As one goes up, the other goes down. And on a scale of negative 1 to positive 1, it's a 0.41. Okay, so that sort of makes sense. And the proof is in the pudding that if we change the scale of 1, I multiply this by 1,000, it doesn't change this at all. So that's exactly what we want. This is a normalized covariance. It just is a way of getting an objective number out of this relationship. This formula is usually not called normalized covariance. It's usually called the correlation coefficient, or Pearson's product moment correlation coefficient, I think. So if I do this again, I've got correlation between x and y, and I've got cove normalized x and y, and you can see they're exactly the same. So this formula we built up from just adapting the variance formula for two things is what correlation is. And so if you ever are trying to figure out why isn't a correlation, all it is this. It's the covariance divided by the scale. So we can calculate it against x and y and z. And if we square it, well, let's look at this example here. I've got uniform numbers, uniform random variables x, and uniform y, and then I make z, which is the sum of the two. So you sort of could expect that z is going to be half of x and half of y, half the variability of x and half the variability of y, because these are both uniform and identical. And so if I calculate x and y, their correlation is 0. But if I calculate x and z, their correlation is 0.7. If I calculate, the same thing as if I calculate y and z, their correlation, curiously, is almost the same, 0.7. So what does this 0.7 indicate? So it turns out that if you square the correlation, you get a value that we often call r squared. It's the correlation squared, and you can see it's 0.502, and that's really close to 0.5. Half of the variability of z comes from x and half comes from y, and the correlation squared is about 0.5. If I do correlation yz squared, it's 0.499. In fact, these probably xz and these add up to almost exactly 1. And so the correlation squared, or r squared, really is a measure of the relative amount of variance accounted for by any variable with any other variable. And so if you take the square root of 7, or square root of 0.5, you can see it's 0.707, which is basically the same as these correlations. So if you take these squared, you get 0.5. If you take 0.5 the square root, you get these correlations, or roughly this correlation. So this is really handy. Another handy thing about the correlation coefficient, that if you square it, you get a measure of the amount of the amount of the variance in one variable that can be explained by another variable. Okay, so this gives us the correlation coefficient, but we're trying to do inferential statistics, and so we want to ask, well, is this thing I observed likely to have happened under the null hypothesis if I had just sampled this many points? And so you could guess, if I only sample a few points, let's see, if I sample a plot of R unit 5 and R unit 5, well, that looks like a strong negative correlation. There is no real correlation in what I'm sampling, but if I just sample 5 things a bunch of times, that looks about 0, that looks about 0. And if I were to calculate the correlation here, negative 0.34, it's negative 0.4, that seems pretty strong. 0.14. Sometimes I get 0.7, sometimes I get large values, sometimes I get large negative values. I could get almost any value here. And so if I only have 5 values, it is not very compelling that I have a correlation of 0.5, because I'm pretty likely to get that. So I would like to know what's the null distribution of correlations, and can I test this? So there's several ways of doing this, and the core test function in R provides a statistical test of the product moment correlation. And so it's going to depend on how many observations you have. We've got a core test of x and y. And it transforms it to a t-test. And so here we see that for x and y, which are created with 1,001 points, and they have a fairly strong relationship. If I were to plot x and y, you can see they've got this strong relationship. Well, this is highly unlikely to have happened just by chance. Now, but the one thing to note about correlations is if you don't have variation, you can't have covariation. So if I were only, even if there were this relationship, if I were only sampling x values here, I might right in this range here, might not see a correlation, or that correlation might change. So if I were to sample across the whole range, if I only had 50 or 100 to sample, it would be better to sample across the whole range than one little slice. And So for example, if I sample just 1 to 100, which is this first slice here, there's no correlation between x and y here. But if I sample 100 spread throughout the x range, that's what this sub 2 is, and I do this core test, I still maintain a strong correlation. So you should recognize that a correlation really depends on what you're sampling as well. And if you have a limited range of sampling on one, you may get a limited range on the other and not see it even if it exists. Of course, sometimes you want a limited range. So for example, if you want to see if some manipulation impacts intelligence, the best way to prove it and maybe even prove it falsely is to find a big range in intelligence. So if you want to look at if there's a correlation between your measure of intelligence and some other measure of intelligence that's objective, maybe you sample children across from 5 to, or for 3 to 10, and you can see, well, look, I've got 3-year-olds that can't do it at all, and they can't do my test at all, and I've got 10-year-olds who do really well on this test, and they do really well on my test. So you might induce a really strong relationship, but if you're trying to then use it to figure out which 10-year-olds should go on to the better school that has better math education, this might not be good at all. There might not be a relationship within a small range, but within a large range you might see one. So there's sort of two sides to that coin. You can't, and like the maximum people say is you can't get covariation without variation. So you have to understand that the variation is needed, but it also may help induce your covariation and not be what you're really trying to generalize to. I think this just shows an example. If I could only sample 100 points here, this red region I don't see any correlation, but this, if I look at the blue, I do see a correlation. This shows some of the variability you might see if you do a subsample. So this is all going to be for the same values, but for the same original values. But if there's, and they have a really strong correlation, but sometimes I see something as small as negative 0.47, sometimes I see something as large as 0.66. So it really depends on how many things you're sampling, and you should understand how variable it can be, even if you have 50 observations. So even with 50 observations, you can be pretty confident that if you have 50, if there's a positive correlation, you're going to see it, but your confidence interval around those is going to be fairly large. Well, how large could it be? So here's in our case, I'm going to calculate the correlation for sampling, in this case, 20 items from this 1,000. So we know there's a correlation. I'm going to randomly sample 20 each time. And it's actually, let me zoom in. So our initial correlation was really around 0.5 or something. And we can see on average we get around 0.5. But sometimes we even get positive correlations if we're just sampling 20. Sometimes we get really high correlations. The true correlation was in here somewhere. And we rarely, maybe 10 or 15% of the time get a value that's close to the true correlation. So although we can do a test and be convinced that the correlation is different from 0, and we would sometimes we rarely get a value different from 0, you have to be cautious about, if I calculated two things and the correlation was higher in one than the other, I'm not, if it's only 10%, 10 points different, I'm not going to be convinced that they're different at all. Okay, so the core test gives us the Pearson correlation, p-value, and this is, the equivalent of parametric test generally. But what happens if I just change one value? So here I've got things that are just barely marginally significant. If I would plot, plot X and Y. There's a small correlation here. But what if I would change just one value? Well, there's actually no real correlation. These are independent, but it looks like it might be slightly positive. And if I do this, you can see, oh, 0.069 is the p-value, the correlation of 0.18. What if I change one value and then make this plot again? Look at that. All of these are clustered around here, and I get this one point way up here that's really strong. If I do this correlation, now the correlation goes to almost 1, almost perfectly because of that one value. So the correlation coefficient can be really sensitive to outliers. This may not be an outlier. I mean, this might be your effect. You might have found the one thing that makes a big difference. But it can be really sensitive to outliers. And things like, let's see. Okay, let me recalculate some x and y values. So, and it also can be sensitive to skewness. So here's a x value and y value where I have made x kind of skewed. Most of the density is way down here, but it has a long tail. And there is an alternative to the Pearson score, which is called the Spearman's correlation. And all that the Spearman's does is it calculates a Pearson correlation on the rank order rather than the absolute value. So this would be the equivalent of a non-parametric test of correlation, because it doesn't assume, so it doesn't punish you that much more for having huge differences, because all of these will get sort of stretched out to be equally different when you place them in the rank order. And you can see here that in this case, the Pearson correlation was smaller than the Spearman correlation because it was sort of influenced by this long tail. You can get the Pearson correlation by using method by using method Pearson, or you can get which is the default in the core function, or you can specify method Spearman if you want the rank order Spearman correlation. And as you can see here, the core test of rank x, we get the same values. The only difference is if I give it rank, I get the same correlation coefficient and the same p-value, but I get a different statistic here. All right. Okay. So one last thing, if you've got a bunch of variables and you want to visualize their differences, you can often use the pairs function to visualize all the pairing. And this is the iris data set. It measures 3 kind of species of irises, flowers. That's specified by the color here, and correlates different measures of the 4 different measures of the flower, the petal size, and things like that. And so you can visualize all of these. And in fact, if you load the ggally and the ggplot functions, which I don't even have on this computer, you can get a really cool looking visualization, and I'll just bring it up from the book so I don't have to load those. So this will give you all the scatter plots plus induced histograms plus correlations with subgroups, bar plots, and things like this. So it can be really informative, and it almost never formats right because things get cut off, but you have to play with it a lot to get things right. But it'll tell you the correlations of all of these. It does not tell you the significance of the correlations, though. So and if I just do core of iris, it gives me, well, I can't do core of iris on its own because iris has this categorical variable. So I can do core of iris 1 to 4, columns 1 to 4, and it gives me the correlations. So I can see some are large and some are very small. But I can't really get the p-values. But what I would often do would be to make a little for loop to get these. And so I loop through all the I values and all the j values that are 1 plus I up to the thing I want. And so I only get each value once. You could even do I in 1 to 4, j in 1 to 4, and then run the core test for each one. And you can see that I've printed out every single pairing, and I can get the t-value and p-value there. So I've never found a all-in-one function that will give me all the cross correlations and their significance. But you could also do this with alternative tests. The last thing is certainly we can do a Bayes factor test too. In fact, I think originally the Bayes factor library didn't even have a correlation test. But instead of doing this core test, we could do the same thing, but it's going to be the function's called correlation Bayes factor. Okay, and here we see that the Bayes factor can be very large. This is scientific notation, so it's got 1.2 with 80 zeros behind it, 5,000. These are all very large Bayes factors when testing these differences. And so there's a simple way of reporting the Bayes factor of these correlations as well. All right, so that covers t-tests and correlations. I'm going to stop here and do one last video covering categorical comparisons, just to have a short break, plus some other issues that we'll cover in this chapter.